Hi guys, Mr. Jenkins here with our first lesson in Chapter 7, which is Section 7.1, Exploring Exponential Models. So we've previewed this just a little bit in our DMR, some of our DMR mixed review problems. What does an exponential model look like? So first of all, an exponential function is a function that looks like y equals a times b to the x, where a is a number other than 0, and b is greater than 0, so your base is greater than 0, and not equal to 1. All right, so let's just jump right to it then. Example 1 says to just graph the following exponential functions. For now, we will lean on our graphing calculator. All right, so for 1a, we want to graph y equals 2 to the x, so I'm just going to type what I see, 2, caret key, input variable or x, and we can look at the graph. We're not going to see a whole lot, but we do see that exponential growth curve. And what would be interesting is if we continued to look to the left, like if we went to negative, 25,000 or something, what we would see going on down the line. Okay. So let's go to the table as far as getting some actual points we can use. So I'm going to hit second and graph to look at the table. Now, I'm going to include anything that I can kind of fit on my graph and that kind of works. So let's include -2 and 0.25. Obviously, I could write in -4 and 0.0625, but just for the purposes of graphing, -2 and 0.25 works a little bit better. So -2 goes to 0.25. -1 goes to 0.5. Let's skip over that one. Go to 0 goes to 1. Let's see, 1 goes to 2. Let's skip ahead a little bit. Let's say 3 goes to 8. Just picking some random points to put on here to kind of get the feel of the shape. That's 5, 6, 7, 8. And we can't fit 64 on there, so let's go to 5 goes to 32, and then that'll give us a good outline of what this graph looks like. 5 goes to 32, here's 30, 31, 32. All right, and then we just want to trace our curve as best we can. Obviously, not going to be perfect there. Okay, so if you were graphing this on a test, you would actually, and you don't know this yet, but you would actually want to include this imaginary line. It's called an asymptote, coincidentally, one of my favorite math words. But it's an imaginary line that the function is never going to cross, but it's going to keep getting closer to. So your asymptote in this case would be, sorry, I meant to make that a dotted line. Your asymptote would be, can't tell that's dotted now, but it would be the x-axis. Okay, so you would kind of include that on your graph. All right, it's an imaginary line that this is never going to cross. All right, so let's go ahead and just look at the other one as well. 3 times 1/4 to the power of x. I'm going to clear that one out. 3 times, and then 1/4. Let's see, if we're going to use an exponent, you do want to use parentheses there, or call it 0.25. I'll just call it 0.25 to the power of x. In other words, you don't want to do 1 divided by 4 to the power of x, because that's something different. So we can see how this is kind of flipped. All right, so this is a different type, but let's go to see what points we can fit on our graph there. All right, so obviously -4 goes too high. -2 even goes off of our graph, so let's start at -1 goes to 12. And just put a few more on there. -1 goes to 12. 10, 11, 12. Says 0 goes to 3. We have that 1 goes to 0.75. And after that, it gets pretty, the numbers get pretty low. So that's where you're getting closer and closer to that asymptote. So I'm never going to cross the x-axis on this one. And again, not that you should know that from what you see here, but I'm going to make my imaginary boundary line here that's not going to go across. And then I'm going to trace my curve as best I can. All right, so again, just kind of leaning on our graphing calculators there. Now, let's make some, go down to the bottom part of this first page, and they make some nice generalizations for you here. So basically, we have two types. One is exponential growth, which we saw in the first example as x increases, y increases. The other exponential decay as x increases, y decreases. All right, so what's going to cause that is, well, exponential growth happens when b is greater than 1. Okay, exponential, and b stands for the base, and then exponential decay is going to happen when b is between 0 and 1. Okay. So in other words, b is like a fraction, okay? It says it right there, but I guess I just wrote it back out. They talk about that asymptote there, and remember, that's just an imaginary line that our function is never going to cross, okay? So moving on. Now we're going to dig into just looking at the equations and not as much the graph, and talking about things like growth versus decay and y-intercepts and whatnot. All right, so it says compare y equals 3 times 4 to the x to the function y equals ab to the x and complete each equation. So what's a equal to? A would be equal to 3, b would be equal to 4. The value of b is one of these two cases, between 0 and 1 or greater than 1. So b is 4, which is greater than 1. Since b is greater than 1, that represents an exponential growth curve. So if we graphed it, we know it would be this shape right here versus this one. All right. And then the y-intercept is, and then they give us basically a multiple choice. So your y-intercept is in the form 0, a. All right. So since a is 3, and then our y-intercept is 0, 3. Okay, so let's just look at a couple more quick ones like that. So if it's growth or decay, we'll use D for decay, G for growth, and then name the y-intercept. All right, so looking at this first one, B is 5. 5 is greater than 1. This would be growth. All right, sorry about that. This is when I normally go to lunch. And then the y-intercept is going to be at 0, 3. And if you ever forgot, you could just type it in and just see, okay? Then looking at maybe the next, or sorry, I'll skip the next one, leave that for you. Let's look at y equals 35 times 1/3 to the x. My base there is between 0 and 1, so that would be decay. All right, and my y-intercept would be at 0, 35. Okay, so those are just you being able to identify some key features of the graph without really looking at the graph or using Desmos or your graphing calculator. All right, so you'll definitely have a test question like this, modeling exponential growth or decay, and it kind of shows you how to set it up. A equals little a times the quantity 1 plus r to the power of t. And they tell you what each variable means. So our output variable is the amount after t time periods. Little a is the initial amount, r is the rate as a decimal, and t is the number of time periods. Okay, so based on that information, let's try to match up a couple of these with their scenario. Okay, and obviously you'd be looking for key numbers here. But it says you buy 50 mice, that'd be your initial amount. Every month the population increases by 15%. All right, so initial amount is 50, or little a is 50, and my increase is 15%. So in the parentheses, I want 1 plus 0.15. So we're looking for one that says 50 times 1.15. So that would be this guy right here. And then let's just do maybe, say one more. Let's see if we can find, okay, this would be a decay one. You have 1 pound of dog food. Your dog eats a quarter of it the next day. And each day afterward, the dog eats a quarter of what's left. So this would be decay. So our initial amount is 1. And then our A is actually going to be negative 0.25. So here we're going to have 1 minus 0.25. So we want 1 and then times 0.75 is what we'd be looking for. So this guy right here. And then I'll let you try the next two. Okay. All right, so example 4, this is getting to the end of it. Now we're going to apply what we just learned there to basically go through a word problem. Suppose you invest $500. That'd be little a is 500. That's my initial investment. Into an account that pays 3.5% annual interest. So that would be obviously my rate there is 0.035. How much will be in the account after 5 years? That would be t equals 5. So an exponential growth model applies to this problem because the amount in the bank increases or decreases. It increases, all right? So that's why it's keyword growth by a fixed percentage of 3.5% each year, okay? All right, so the initial amount invested, or A, is 500. The rate as a decimal, 0.035. And so my equation then is going to be 500 times 1 plus 0.035. And then we make it look pretty. So my final equation is going to be A of t equals 500 times the quantity, 1.035 to the power of t. So that's my model for any number of years, and then we're going to use that model to evaluate the function for t years. So that'd be 500 times 1.035 to the 5. So let's just punch it in. 500 times 1.035 to the power of 5. And that gives me 593. And then it's understood here that I would round to the nearest hundredth because we're talking about dollars and cents. So about 593.84. So I'm going to change this since we're rounding to about 593.84. All right, so that does that one. The next one, I'll go a little bit quicker on because there's a question I wanted to kind of get to. I may not even, well, let's go ahead and look through this one because this one's a little bit different. So here we're investing 500, still pays 3.5%, but the question is different. the question here is, when will we get to $650? So we know it's sometime after 5 years, because 5 years gets me to just over 590. So really here what we're asking then is 650, because that'd be my A of t, equals 500 times 1.035 to the power of t. All right, so my question for you was going to be, could we solve that algebraically? And like if I told you to round to the nearest, say, hundredth of a year, right? Do we have any better method than guess and check? And the answer to that is no. We don't really know how to solve equations that have a variable as an exponent. So the best we can do is just kind of guess and check, or I'll do you one better. I'll use my graphing calculator. Okay, that's what I'll use. All right, so let me just type in 500 times 1.035 to the power of, we call it t, on your calculator you'll call it x. All right, and then let's set our window. Let's do another function of just y equals 650, and then let's set our window to where we can look real high on the y-axis. At least 650. Let's go to 700 and say count by 50s. All right, so when does this point of intersection happen? And notice that my growth curve looks a little less drastic, and that's because I'm counting by 50s here, and I'm going all the way up to 700, right? So there's a couple ways we could do this with our calculator. We could look for that point of intersection if we wanted to, or I think the simplest way to do it would be just to look at your table. So if it's second graph, and then remember I'm looking at the blue function. So when do I get to that 650 mark? So remember our 5th year, we got to 593.84. We kind of did that algebraically. 6, we get to 614 and change. 7, 636. And then in year 8, we go over 650, right? So we can tell by looking at this that it happens sometime, by year 8, we're over 650 is what we could say based on this. So a good answer to this question, based on the knowledge we have right now, would be we could say approximately 8 years, or by year 8, we have, you might say, at least 650, or we go over the 650 mark, okay? Which specifically we go to 658.40. But like I said, we really don't know how to get closer than that based on what we know. In other words, we couldn't really solve for t. So we leaned on our technology to do the best we could. All right, so anyways, that is basically what you'll be looking at in 7.1. As always, I hope this helps, and you guys will let me know what kinds of questions you have, I'm sure. And remember, this is the start of a new unit, so always good to get off on a good foot. Thanks, guys. Have a good one.